With that, I'm thrilled to introduce our first speaker, Anandkumar, who I just want to say has been a mentee of mine for over a dozen years, and I am deeply, deeply proud of having her as my mentee. Anima is the Bren Professor at Caltech and a pioneer in using AI for scientific modeling and discovery, including breakthroughs in weather forecasting, drug discovery, and engineering design. She invented neural operators, a deep learning framework that enabled the first AI-based high-resolution weather model, transforming the field of AI-driven climate science. Please join me in welcoming her to the stage.
Thank you. Thank you, Jennifer. Thank you, Chrissy, for the generosity, for your vision in really bringing all of us together here. To me, AI and science coming together has been a long dream, and we're seeing so much of it come to fruition now. Having been at Caltech for almost a decade now, when I started at Caltech, there was a lot of excitement around AI, and at the same time, healthy skepticism, right? I mean, there's data available on the internet with text and images, but how can it really impact science where data is not as plentiful? There are lots of gaps, right? People go deep into one specific topic. How can AI touch all of these different areas? And so going to Caltech, that was my mission on, can I go and talk to almost every faculty, understand what their challenges are? At that point, I was at Amazon Web Services, so that was a great way for me to bring in cloud credits, think about how computing could touch every area. And so that's how I got introduced to so many professors and so many challenging problems. And fast forward today, we are in this era of language models. It's made tremendous impact, and it's also impacting science now. You're going to hear many talks on how language models are helping with scientific discovery, right? Not just to look up for facts, but also to become agents. And one time, will it become really autonomous and help make new discoveries? To me, that's one ingredient of scientific discovery, right? Coming up with new ideas, coming up with new hypotheses. But we cannot just stop there, because ideas are just the beginning. What makes them happen are the experiments and observations. So you really need to go to the real world, go to the physical experiments, do them. And anybody who's an experimentalist here will tell me, oh, that is really the hard part, right? I mean, especially in chemistry, material sciences, we know the hard part is not that there is a vast universe of possible molecules, but how many of them really work out in the real world. And so the question is, can AI also impact that? If we have more confidence in these discoveries, if we can validate them in the digital realm, so essentially run virtual experiments that you can trust, that is physics informed, that is physically valid, then you can take only the winners to the real world, do a few experiments, and come up with success. And so to me, that's the aspect I will really touch upon in this talk, how we can push the frontiers of science by enabling AI with physical understanding. Understanding of this physical world at different scales in different domains so that we can minimize the need for physical experiments and have it make discoveries that can really be impactful. And so to me, this kind of physical understanding happens at multiple scales, all the way from the atomic scales where you have quantum level effects to proteins. How do drug molecules bind to protein targets? And ultimately, there are many phenomena that may even happen at the planetary scale, like weather. If we are suffering from flu or COVID, it's like the weather has an impact, right? So maybe locally, maybe more globally. And so you have like all the way from atomic scales where the coronavirus, how it binds with targets in our body, you have to model that, and you may have to go to planetary scales to understand the impact of weather and climate on pandemics. So all of this has to come together for us to make a full understanding in that specific case. And so you can think many applications, chemistry, material science, require this atomic level understanding. And then you have like what we call continuum mechanics, like fluid dynamics, that impact weather modeling, that impact the design of airplanes, rockets, drones. And so you have so many different areas of science and engineering coming together, but ultimately there are unified mathematical underpinnings, right? They may look very disparate. I'll show you lots of different domains, but to me the unifying aspect is there is mathematical equations that describe these different scales of interactions. We may not have as much data as on the web, not as many images or text that corresponds to more natural language, broader discussions. We can't generate as much data in these areas, but we do have mathematical equations. So you could simulate some of this through computational methods. You can have some experimental data, but you can also embed that knowledge of physics into AI itself and bring all that together. And to me, that's really the vision of how we can build this AI with physical understanding. First in like maybe parts of these different scales of interactions, and ultimately maybe even span that wider and broader. So to do that, as I mentioned, these multiple scales of interactions require computational complexity. They have high computational complexity. For instance, with weather and climate modeling, depending on how much you zoom in, right, what resolution you measure the phenomena, different phenomena occur. Some of them require lower resolution, like for instance, atmospheric rivers that impact California here occur thousands of miles wide. On the other hand, if you want to ask, what's going to happen with climate change several decades from now, the biggest uncertainty comes from these low-lying clouds, and you need a very high resolution to resolve all the scales there. And in fact, my colleague at Caltech, Tapio Schneider, estimates it's more than 100 billion times the computing power we have today. Because sometimes people are worried we are building all this compute, what are going to be the use cases if language models top out? And I tell them, oh, give me all that compute. We can do science, and we can do lots of it. But of course, so many of these are untenable, right? If you look at chemistry, it is Schrodinger's equation. Trying to brute force compute and solve the Schrodinger's equation in a molecule of just 100 electrons takes more than the age of the universe. So these are these impossibly hard problems. So in a way, we know all of the universe because if we believe those equations, and there's a lot of proof that we can believe them, we've solved them. But that's not enough. It's not just about knowing what the physical phenomena is in terms of equations. We really need to be able to solve them, simulate them, to be able to make new discoveries. And since doing that with traditional computation is so expensive, can we now bring AI to accelerate that? Can we speed up those simulations with AI so that we can not only run them faster, we can run them in many different scenarios and be able to make new discoveries, be able to come up with better confidence of various phenomena like climate change, really get to the resolution so that we can think about regional effects and come up with policies. And that's where neural operators have been very useful in thinking of these multi-scale phenomena. So if you think about text, you assign a token based on the vocabulary, right? So you already know what are the possible words that occur in English language, and that's how you can design your neural network. Standard images, so if you go to Gemini or ChatGPT, look at image generation, you fix the resolution, you train the model, you generate in the same resolution. But as I showed you in the previous slides, that's not enough for science, because physical phenomena occur at multiple resolutions and scales. So you cannot say, oh, I already fixed my number of pixels, I'm going to do all of my modeling just there. Because if I then try to zoom in and say, oh, no, there's more details I want to add, it just gets blurry, right? That's not enough. And that's why standard modeling that has been successful in text and images is not directly enough, right? You need to add a bit more, and that's what we did with neural operators, where we said, let's have a way to keep zooming in and keep the sharpness. And so we've thought about now the world not as discrete tokens, but as continuity, meaning you can keep zooming in, and you can keep coming up with answers, you can keep giving it more constraints into the model at any resolution. So the analogy I like to also give, especially for people in graphics or who know graphics, is raster graphics versus vector graphics, right? Raster graphics is fixed number of pixels. You zoom in, there's no more sharpness, it gets blurry. Whereas vector graphics means you have like a functional form, meaning it's a continuous function. You can keep zooming in, you can retain the sharpness. And neural operators enable us to do that, and we can add physics at different levels. We can add data at multiple resolutions. We'll see many examples, like in the weather models, in chemistry. You may have data at multiple resolutions and multiple levels of approximations you've collected. What if you could bring all of that into one model? And one model doesn't mean one layer. It can be multiple layers and have that complexity. But you really have this seamless way of collecting data at multiple resolutions and bringing it into one AI model. And that's what neural operators enable us to do. And so why is this important? You'll see in a number of areas, you really need these fine-scale information, right? So I've shown these cloud phenomena here. Why is it just not enough for me to stare at a hurricane and tell you where that goes? Of course, Trump may be able to do, but mere mortals like us cannot. And the reason is because you need to zoom into the fine scales and really model the Navier-Stokes equations and be able to do that prediction. And so resolution matters, and neural operators can help you get to any resolution that you would like. And so let me show you some examples of how we've applied them in a number of areas. So as Jennifer mentioned, in 2021, we created the first high-resolution, full-complexity AI-based weather model. By that, I mean it was able to predict phenomena like these atmospheric rivers, right? So this is a global phenomena. It's spanning thousands of miles, and we wanted to see how well it can do. And to our surprise, even the first attempt, the good news was there was open source data set available. The ECMWF, the European Weather Agency, has made this available. And in fact, they had collected all of the 40 years of data from different satellites, combined it with physics, and open sourced. We could train on it, and then we were able to see that AI is not only doing accurate prediction, but it's faster. It's tens of thousands of times faster. And this really surprised so many weather scientists. Because just a few months before we had released this model, they had even an article saying it would take at least a decade or more for AI to make an impact in weather modeling. Because they thought, oh, this is such a complex phenomena. This requires all of this knowledge of physics, and you need to solve the equations of physics from the bottom up to try and predict weather. Instead, what AI is doing is a more top-down, right? Meaning we have data available, it's learning patterns implicitly. It has the knowledge of physics, but it's implicit rather than explicit. And still, it's able to do so well. And now The best way to make an impact is to open source the model. Ours was the first openly available, permissively open sourced, meaning startups, commercial entities, everybody could take these model weights, do their own modeling, and that's what is democratization, right? Really enabling everybody to take weather models, bring in their own data. A lot of local weather agencies, for instance, in Taiwan, in India, many other places were able to harness this. And it's also available in the ECMWF website. So if you go there, you can look at 2-week weather forecasts every day. And that's what increased the confidence for weather scientists, because they could see it in action, and they see that it's not only doing well in typical weather. We are in California, well, maybe not in San Francisco, but the rest of California, it's pretty easy to predict weather for most of the time, except a few days. The question really is the extreme weather events. Right? And to the surprise, even extreme weather events like hurricanes, this example is Hurricane Lee, where our model ForecastNet, you can see in orange, is able to predict landfall and do that earlier and more accurately than the standard weather model. So just because AI is faster doesn't mean it's less accurate. In fact, it's both accurate. Now, the latest versions are even more accurate than traditional weather models, and also doing well on extreme weather events. But a machine learning person would ask, how is this possible? There are so few hurricanes in the data set. Over the last 40 years, there are not so many. So it's not so surprising if you do well on typical events, but not extreme events. So it turns out, in a way, physics is hard, but physics is also easy for machine learning. Maybe not for us humans, but for AI. And that's because hurricanes have this physical signature of hot and cold air mixing, which is a pattern that AI can really latch on very well. So you may not need as many samples as you think you need. Just because language models require this enormity of internet doesn't mean so much of science needs that. And that's been our experience repeatedly, that you can get away with fewer samples, especially when you think about designing better AI, physics-informed AI that can harness both physics and data together. And so that's why maybe it's not as pessimistic as we thought in the beginning. Oh no, science doesn't have as much data as these other domains. So we may be still lucky, and in this case, this is a really good stroke of luck. And so what scientists care about is not just us getting lucky on one hurricane, but really being able to prove that we have good confidence in our predictions. Because science is not just about making a prediction, but being in a way humble, right? Being in a way calibrated, what we call the confidence level should align with the ground truth. So in this case of hurricanes, truly you can never be perfectly accurate in predicting them, because it's what we call a chaotic phenomena. So if you've heard of the butterfly effect, if you try to predict it early on, for instance, hurricanes starting here in the Caribbean, more than a week or so in advance, it's you could get it very wrong because it's chaotic. So small changes in the initial conditions can completely throw off where the trajectory goes. So what you can instead ask is, I cannot perfectly predict the trajectory of the hurricane, but can I instead give you statistics? What is the confidence level of where the hurricane may hit you? And so what you do is you perturb. So you make small changes to the initial condition and ask, where will the hurricane go? And by collecting so many scenarios, now you can say, how many of these tracks hit Florida, a specific region in Florida? And so if you have a large number of them hit that specific area, you now have a high confidence the hurricane is going to make landfall there. And so that directly impacts the policy decision making. Should there be an evacuation? What level of warning should I give to the population here? So people really care about not just predictions, but this what we call risk assessment. I mean, same for wildfires. Our community at Caltech has been severely impacted by the wildfires earlier this year. So if we can improve all of those risk assessment of which areas are going to be more impacted than others, that is very valuable. And that's also valuable for these long-term climate change, right? Because you can never perfectly say what the weather will be a year from now, let alone 50 years from now. But we can give these average statistics and come up with policy decisions. And this is where AI is really making a big difference, because the speed up directly translates to better risk assessment, better calibration of these kinds of extreme events, so we can be better prepared whenever the next such catastrophic event strikes. And so this is where AI is not just enabling the current weather, for the next 2 weeks. It's also enabling extreme weather events. It's enabling risk assessment. And it can also now do longer rollouts and enable climate modeling as well. And this is where it's useful to think about how AI incorporating more of the knowledge of the domain helps. So what you see here that blew up was an AI model assuming the world is a rectangle. I mean, of course, the world is not a rectangle, right? Whereas the one on the right is showing that the world is a sphere, and it's building that into the model. Meaning the model knows that the globe is a sphere, and you're making predictions on a sphere. And if you keep now running this model, not just for the next day, but for the next year, the fact that it's a sphere is important, because that's what enables us to keep that spherical nature and not have these what we call blow-ups. So blow-ups are bad because now you can't trust this model for climate, right? You can't do very long predictions and still have it give meaningful results. And in fact, this is not just with AI, with traditional weather and climate models. To my surprise, weather and climate community don't talk to each other much. They have completely separate models. And I was like, there's only one Earth. Why are there multiple models? But AI can now really build these truly foundation models for both weather and climate together, right? Because you can have these short-term forecasts be accurate, but you also build in information like the Earth being a sphere and many other right physics. You can also keep running this for longer and make it a climate model. And in fact, my colleagues at Allen AI Institute have done that. So they've been building climate models on this same architecture. And so now we can kind of bring in the current weather information, the future climate change aspects of how that would make changes, and put all that into one model. And that requires not only data, it requires the knowledge of physics, because we don't have the climate change of tomorrow. We need to incorporate physics into these models, and that's where there's exciting work happening. So there's many other areas, in addition to weather, where we are seeing similar impact by modeling these kinds of multi-scale phenomena. This is the example of nuclear fusion, the tokamak reactor in the United Kingdom, and with collaboration there, we are able to model plasma being 1 million times faster than what we could do with traditional simulations. So we can run this faster than real time and be able to predict disruptions before they occur, because that's a big bottleneck in making nuclear fusion possible and tractable. And so there's a lot of interesting questions of how we can take more experimental data from the tokamaks, our knowledge of physics and the equations from magnetohydrodynamics, and bring them together to make plasma modeling possible. And other areas like climate change solutions, in this example with Stanford, collaboration with Stanford, we were able to look at how carbon dioxide can be sequestered or stored in the underground reservoirs. What is the pressure buildup? And if I store them for several decades, where will carbon dioxide move? How much will it escape these reservoirs? Because if it goes back to the atmosphere, there's no point, right? So you really need the ability to keep them underground. And so it gives us the ability to make these modeling faster, almost 1 million times faster, so you can do high-resolution modeling. And many companies like Shell, ExxonMobil, others are using this information because they have a lot of reservoir information, but they can use AI to do very accurate modeling and plan for carbon sequestration efficiently. So it's not only that we are doing forecasting and modeling with AI, because these neural operators and other AI models are differentiable, we can do inverse problems. And one such inverse problem is inverse design. So in the case of designing semiconductors, even quantum devices, what the challenge is, what is the best design that we can do? Because fabrication, going out there, doing these physical experiments is expensive. So can we just first have AI design this while keeping the knowledge of physics? And in the first example, what we are able to do is much better mask design. So the big bottleneck in being able to miniaturize semiconductors, go smaller and smaller so we can pack more in a space, right, have better chips for AI, is lithography, right? So the lithography is the process where the mask design is important, so having the right shape of the mask will enable us to have more accurate chips. And we were able to do that, sorry about that. I thought there was a video, but anyway, we were able to progressively have AI learn better and better design and improve that. Another example is quantum dots, where it's even more difficult to come up with chip design because you have highly nonlinear effects. You want to pool the electrons in a small space and have many gates try to act in unison to do that. And AI is able to do that. And what my collaborators tell me is no human was able to solve this because it was so complicated. And I think that's a message we keep seeing again and again. In these kinds of very complicated phenomena, humans are not very intuitive, right? So this is not something humans can intuitively design. But for AI, because it understands this physics in these multiple scales, it can come up with the best design while incorporating all of the manufacturing and other realistic constraints all into the optimization problem itself. So you can not only do it for one scenario, you can do it for many different scenarios of manufacturing and design. You can also do control, so meaning once you learn about a physical phenomena, you can now control and overcome issues like turbulence. In this example at Caltech, we were able to ask how we can stabilize the wing in a wind tunnel. So under high-speed winds, can it learn how to stabilize? And we put like flow sensors so it can sense how much the flow is, come up with predictions of how turbulence will change. And our model that, again, uses like Fourier-based methods that is very intuitive for turbulence, it can do that much faster and more efficiently than other reinforcement learning methods as well as traditional control methods. And it need not be just in a fixed wing, it can also be like drones, right? And at Caltech, we have really the privilege to have these kind of facilities where we have an array of fans, so they can come together, we can program them into all kinds of wind conditions, so we can really test how they can fly under turbulence. And so hopefully one day, we can have drones go out there in these high-speed wind conditions that we saw for the wildfires earlier this year, because no aircraft or helicopter could fly back then. So that's really the goal of CAST at Caltech, which has this collaboration from multiple areas to enable such drones in highly challenging conditions. And AI is important because we can both learn offline, we can learn on simulations, we can learn on real data. And then there's also online learning and control because you still have to adapt to the current conditions. You can't just rely on the offline data. And all of this can be enabled to come together. So I want to show you some examples of what we can do in the area of medicine. And so one example that has been really an important problem that I was not aware is how in hospitals, the most common infection is from medical catheters. So if you're in the hospital long term, you're very likely to get an infection. And in fact, it's a simple concept from fluid dynamics that bacteria tend to swim upstream along the wall and get into the human body. And so the question was, can we understand fluid dynamics and train AI to overcome this? And it was a very simple design principle, a passive design where we can have like triangular grooves, so very small triangular grooves, 3D printed inside, and then we can ask what is the optimal design. And so AI was able to optimize the design directly. As I mentioned, AI is differentiable, able to do this. And this is now lab tested. And what you see is all the bacterial particles are pushed outwards, so they're not able to swim upstream. There's only, I think, one here trying hard to swim upstream. So what we saw is like 100-fold reduction in bacterial contamination. And in this example, all of the design was done digitally with AI, and the lab testing was done only once. And that's really the promise, right? If AI could kind of iteratively improve design digitally, you minimize the requirements for these physical experiments. And also for medical imaging, AI is really important because you can both reduce the sampling rates in areas like ultrasound imaging, functional ultrasound in the brain. If you could do that real time and make it faster than real time, in fact, collaboration with the Chen Institute, we're able to show that we can greatly speed up our ability to do behavior decoding and other examples. So many different speed ups. I'll just show you some of these examples here. So one is the lung ultrasound, where we're able to really change the nature of how diagnostics are made. Because what is done currently is having a clinician look at these blurry lines. In fact, not the boundary here, but actually what they call these B lines. So you're supposed to say how much the lung is aerated by looking at blurry lines. Instead, we have AI coming up with the actual image of what the aeration levels are. So you have direct, like quantitative information of how much the aeration level is. And so it's changing how you can directly do these diagnostics. And we can also validate them on pig dissections. So on animal dissected tissues, we're able to show that AI is much more accurate than what human clinicians have been able to do with very subjective evaluations, because AI can come up with a direct prediction of the full imaging of the lung rather than blurry lines. In other examples, like photoacoustic imaging with Li Hong Li at Caltech, we are able to show how adding physics to AI together can give us both sharp images, as well as you're really harnessing the physics of how both like the laser and the ultrasound, right, is coming together, the wave propagation information, and using that to improve these predictions. And as I mentioned, the other example is with real-time behavioral decoding and being able to do that very accurately, so having this speed up and maintaining accuracy, because we can now sample things faster, because machine learning is able to understand the patterns without requiring very vast amounts of data. So I want to give just a few snippets from the chemistry domain where AI has also made a big impact. One of the examples where I want to show this multi-scale nature is really in this area of coronavirus, where we got started in the beginning of the pandemic, in fact, where we showed that, if you think about the coronavirus, it's really the spike protein, right, that's on the surface of the coronavirus. And so how much you have binding to the spike protein determines a lot of the aspects, including how infectious this is. So looking at specific parts of the spike protein, and we'll look at calcium ions in our respiratory aerosol, the binding abilities there determines how infectious it is. So going to these atomic levels and being able to do that accurately is really important. And that was one of the first examples of this multi-scale modeling, where we capture different scales of molecular modeling to be able to understand how coronavirus interacts with the respiratory aerosol. And to do this, we incorporated information not just in terms of molecular graphs, but these orbital features. And the Chen Prize winner, Joran, I don't know where he is, he will be giving more details. As one of his first works, he worked on really incorporating the knowledge of quantum chemistry with AI together to have this high level of transferability, keeping symmetries, keeping all this information together really enables, as one of the applications, understanding coronavirus interactions better. And so really these fundamental aspects of bringing together quantum chemistry with machine learning methods can enable us to do not only faster predictions, we have thousands of times faster than what we could do with traditional simulations, but we are also able to do that on larger systems than what it was trained on. So we trained on molecules just almost about 40 or 50 atoms, but these are thousands of atoms. And with standard AI, this is impossible, right? Because training and testing should look very similar data. But now with the addition of physics, we can now bring in more of that modeling and be able to extrapolate and do predictions on much larger systems. And so as one of the last examples, I want to show in protein design, and I know the next talk will cover a lot of that, but just to give you an example of how we can have generative AI do design of proteins, do design and prediction of new variants of concern. One of the examples is how we can have coronavirus, again, in the middle of the pandemic. We were able to predict new variants of concerns before they emerged. So meaning during training, we only showed it the variants of first year, and we were able to show new variants that the model hadn't known, and even the ones that are concerning that may not have emerged, so you can be better prepared. And the idea is this is the latent space of the model. It's able to not only learn this kind of evolutionary patterns of how different variants emerge, and not only for coronavirus, but for all different virus and bacteria. Because we said, let's look at every virus, every bacteria known to humanity. Let's put all of that together into one model. And we use the language of genome, similar to the English language, and train a model. And so we are able to see new variants emerge because it's learned how various different bacteria and viruses mutate, how they evolve. So all those patterns are transferred to new species like coronavirus because there are very similar mechanisms across different bacteria and virus. And the same model is not only useful for predicting coronavirus mutations, it's also useful for designing new functional enzymes. And this is with collaboration with Francis Arnold's group, who's won the Nobel Prize for directed evolution. And so we took an enzyme, tryptophan synthase B, extensively researched, and she challenged us, this is a complex enzyme. Can AI really come up with something here? And what I've shown here is the natural enzyme, so naturally occurring. In her lab and other researchers have done directed evolution, meaning you start with some initial enzyme and you let it evolve and see whether you get better functionality, and that improves in many industrially relevant reactions much better yield. But it turns out our generative AI model with carefully designed physics-informed filters could generate a new enzyme that is better yield across all of these different reactions. So this is what we call a versatile or promiscuous enzyme. So it has many different functionalities across different reactions and with a good yield. It's also thermally stable, which people care about a lot. It can work at 75 degrees centigrade, which is important for reactions to happen. And so this was a surprise that AI is able to beat years of research that have happened with directed evolution in the wet lab. So in a way, it's virtually doing that internally and able to come up with better enzymes. And to me, this is just the beginning, our ability to design for better enzymes, incorporate knowledge of physics, come up with better engineering mechanisms. There's so much that we can be doing in future. So to conclude, I know I covered a lot of ground. It may appear like many different areas, many different success stories, weather modeling, nuclear fusion, medical imaging, designing medical devices. But really, the common theme in all this is the physical world may look complex, it's multi-scale, but AI is able to learn these different scales of interactions. It can take in knowledge from simulations. It can take in experimental data. It can also directly incorporate physics inside itself, what we call physics-informed learning. And bringing all that together means that we can solve these challenging problems. And to me, what is next is really this frontier of scaling, right? So what would a universal physical understanding look like? What are the foundation models for science? And this requires all of these ingredients. To me, a foundation model for science cannot be just at one scale or one resolution. It has to have that flexibility to span multiple scales. It has to have the knowledge of physics, right? Because discovery is about going to the unknown. By nature, it's extrapolation, so you cannot just rely on training data. So it has to be able to go beyond, and that needs the knowledge of physics. And bringing all this together will really help bring scientific discovery even further in its acceleration. Thank you so much.
So,
do you have time for questions?
yes,
Okay,
we have time
awesome,
for
awesome.
questions. So, who would like to ask a question of Anima? You're all just stunned? Over there. Okay. Oh, you can go up to that microphone there and... okay. Well, why don't we let her go first and then you?
Thank you so much for your amazing talk, so inspiring. I wanted to follow up on extrapolation, especially with climate models, because we have a changing climate. The past will not really be the future. So I'm just really curious how you're designing that into your AI models to be able to extrapolate for a changing climate.
Yeah, absolutely. And how do climate scientists do it today, right? So they're doing simulations because they're saying, we understand physics like Navier-Stokes, heat transfer. So you have a set of equations, and right now they're simulating it from scratch, meaning each time you run a new climate simulation, you are generating those simulations from scratch. And so what AI can do is learn across those simulations and be now much faster in that generation. So all those speed-ups that I showed, you can do that with simulated data. But you could go further, right? So you could both take those simulations, you can take the current weather model and further add the simulations for the future. And you can embed some of the physics directly into the model. For instance, the fact that you have heat conservation as an example, energy conservation. So you bring in more, it becomes much more able to do all kinds of extrapolation. So it's really a combination of combining the current observations, simulations, and knowledge of physics, either as soft constraints, hard constraints, into the model. And that's where a lot more algorithmic nuance is needed, right? It's not just a standard kind of recipe that works for every area. So it depends on how many simulations we can generate, at what resolution we can generate, and bring all this together. And people are doing that at Allen AI and many other places, so it's an exciting time for that.
All right, thank you so much.
Okay, next over here and then there.
Yes. Hi. First of all, thank you very much for the talk. It was very broad, very interesting. I was wondering if you could provide a bit more detail on the neural operators you use and how you integrate them into like more standard or common neural network approaches. So
Yes.
you talked about using neural operators to like represent data or process data on multiple scales, and you also talked about like using it for multimodal processing of different data modalities. And I was wondering if you could just give a bit more detail about how that works and like why the neural operator approach is superior to doing something more common or straightforward, like having a linear layer that translates across resolutions or that sort of thing.
So I apologize. I know I didn't go into the technical details because I wanted to show this breadth, so there are many resources online. But really, think of neural operator not as a competition to any existing neural network, right? You can take transformers, you can turn it into a neural operator, just that it may be very expensive. You can use like convolutional neural networks. You can also make it into a neural operator. The idea is, what works in a fixed resolution, you really want to extend it to learning a function instead. And so we have lots of ways to make that happen. But the crucial detail is, it's a mapping from one function space to another. So the input can be in any resolution, the output can be at any resolution. And there are many different architectures to realize that. And the benefit of doing this, we show in many examples, is you can now take low resolution data. So you have simulations that are at lower resolution, they're less accurate. You first train, so you can generate a lot more. You first do the initial training, and then you can add a little bit of the fine scale data. So either data that was collected from observations that is very expensive to collect, or simulations that are finer resolution. And you bring them into one model, you can fine tune that model. And so that way you can be a lot more data efficient because of this neural operator approach.
All right, thank you.
Yeah. There.
Hi. Super interesting talk. I guess something that I'm curious to hear your thoughts on more, I guess at a higher level, is just so at the end you were talking about, okay, we need to kind of have different scales and also to incorporate physics. But I'm curious, there's a lot of very interesting scientific problems that lie in areas where I think at least doing both of those things at the same time is difficult. So something that comes to mind is biology, where understanding an organism, let's say at a more macroscopic level, versus connecting that to what you did show with, let's say, maybe drug protein binding affinity. And like, how do you scale in something like biology where it's maybe not as clean as with the laws of physics? And do you have any thoughts on that?
Yeah. Absolutely. I mean, it's a combination of the top-down and what I call the bottom-up approach, right? The bottom-up approach is going all the way down to quantum chemistry and saying, can I predict the reactions better? Or at the protein level, saying, not just, I do the folding, I do like protein dynamics. Joran will, I know, talk more about that. So you're kind of like looking at specific reactions, specific candidates, like say protein targets in our body, and then coming up with those. And then you may have some limited human trial data or some human mechanism data that says these are the protein targets, right? But there may be other off targets. And from human trials, you realize that once you do that. And so there's again, that's the hard part. We have very limited human trial data. We, of course, have like maybe animal data. We may have organoids. So somehow bringing all that together is harder. So a lot of my research looks at building up more from that bottom-up physics where we have the ability to generate data from simulations. It's just too expensive, but if we have more compute, we can do more of that. But that's why we require biologists, experimentalists to also improve data generation on the other side. I know there's a lot of work on cell perturbation, right? All of that happening. So yeah, so one day all of this will come together.
One more question.
Thank you for the wonderful lecture. You have all the wonderful resources here in the Bay Area. There are people around the world, around the country, who are also interested in participating in this kind of research. So this is also a question of scales and socio-technical systems. How do you see developing the workforce and the connections to make this work expand beyond your laboratory, outside the Bay Area, connecting with other people who have the large data sets that you can work with, who have domain-specific expertise that can help feed into your modeling? In other words, developing a large-scale system to expand the impact of what you're doing.
Yes. Absolutely. I mean, over the last decade being at Caltech and, trying to do this experiment across campus, right? So being a small place, it was easier to go connect with people. And, one aspect is, trying to provide them resources. So, as I said, my story was I go with cloud credits from AWS and ask people, what problem do you want to be solved, right? And so there is then interest on sharing and starting with some prototypes. And so you have to start small and then scale up. But in this era now, so many tools are so well developed, starting with even just search. Language models are able to search papers very well, get all that in a good place. So you can really have students, young people in every domain be AI native. And at Caltech, we've been doing that for a while. We have both the data science major and minor at the undergraduate, graduate levels. And so having every person in different domain be able to not only use AI tools, but be able to train models. And so that kind of common skill set is where we can have these interdisciplinary collaborations. So we need more of that.
Thank you.
Yeah.
I'm going to say one thing in response to that question. I think that one of the most exciting developments of AI is that the platforms that we are building, especially the open source platforms that we are building, can be used by everybody everywhere. You'll hear later today from Omar Yagi, who has been going around for years and years, going to developing countries to try to get young people to be able to do science, and working with their governments and trying to get them to be able to do science. And I think the kinds of platforms that Anima is building, that others are building, I know Omar is phenomenally excited about this as well. She's built an open source platform, okay? What you need is you just need access to the internet to use her open source platform. So really, the age of AI will be a democratization of science. And now I would like us all to thank Anima again for her phenomenal talk and work.